Hi, I'm Jonathan Boccara. I write on the blog Fluent C++. It's a blog about expressive code in C++ with an article every Tuesday and Friday, and I work at Murex. I am a team lead of a C++ developer software developer team. Sorry? You have a microphone. It's not working. Oh, it's okay. Just let me put that up. Hi. Hi. Everyone hears me? We're good? Okay. Right, so I was Jonathan Boccara. I was on Fluent C++ writing twice a week about expressive code in C++, and I'm still working at Murex as a team lead of a C++ software developer team. What we're going to talk about today is the STL algorithms. We're going to start off this talk with a question to you. Who in this room is aware of the fact that it's a good thing to know the STL algorithms? Just raise your hand if you're aware of that fact. That's pretty much everyone hands rising. That's pretty cool. Second question, who knows them all? Come on, raise your hand. Come on then. That's pretty much that's actually no one's hand rising now. That's exactly the purpose of this talk. When you walk out of that room, you will know every single thing that's in the STL algorithms library. To do that, I suggest that we start with a brief chat about why it's important to know them and what to learn in them, and then we dive in the STL algorithms themselves. All right? So there's this thing that's been popularized across the C++ community over the past few years. That's we need to know all the STL algorithms, and we need to know them well, very well. But why? Well, for one thing, they can make our code more expressive. And they do that by raising levels of abstraction, which means that they allow to express what we want to do as opposed to how we want it executed. And I think that raising the level of abstraction is one of the most efficient ways to write expressive code. And it can be sometimes spectacular. Like, if you've seen that talk a couple of years back by Sean Parent, which was called C++ Seasoning, in that talk, Sean took a chunk of code that was a bit hard to understand, and he refactored it into a more concise and expressive piece of code just by picking the right STL algorithm. But that's not the only reason. If we write ourselves our manipulations on collections, then we have to write somehow the traversal of a collection. And we have to write a for loop if we don't resort to using STL algorithms. And when we write for loops, there are things that can go wrong. Like, for example, we need to be sure that the traversal doesn't go past the end. Like, we have to run that mental check, run the loop in our head to make sure, and even then there's a risk. And if we go past the end of a collection in C++, then we get into undefined behavior. And from that point on, anything can happen. Literally, anything can happen, and that's allowed by the standard. What's happening on the screen right now is absolutely legal C++, even though it's probably more likely that you get a crash than a clown popping up next to you, but still, the clown is legal by the standard. Another kind of mistake is dealing with the case of an empty loop, and that's the same thing. We have to run it in our head, have a risk of it going wrong sometimes, and then going to undefined behavior all over again. With the STL algorithms, this doesn't happen. So that's one more reason to use them. Another case of mistake we can make when writing our own for loops is about complexity. Like, some algorithms that they can be implemented naively in quadratic complexity and in a more astute manner in a linear complexity. We'll go back to an example later with algorithms on sets. Also, STL algorithms are used by billions of people every day. Well, maybe not billions of people every day, but quite a lot of people fairly often. More seriously, there are parts of standard C++, which means that you should not be afraid to use them and think that maybe somebody is not going to be able to understand them because they don't know them. I think we should level up to the STL algorithms and not the other way around. So this is part of the common vocabulary of C++, just as much as int or if or whatever in the language is. And it's so standard that even if you're running an older C++ version, you can still get most of the STL algorithms. Like, for example, if you're in C++ 03, for example, and you want to use like all of or any of or none of, which appeared in C++ 11, well, you can just grab that code and copy it into your code base and just start using them. So most of them are within your reach, whichever version of C++ you're right now. Right, so now let's say that you want to go to the STL algorithms, you want to take that path. Well, there's a trap that's lying just at the beginning of that path, and this is called for each. For each is one of the STL algorithms. There's nothing wrong with it. It has a use case, we'll see a bit later. But the trap that it represents is that it looks like a for loop, right? Because it takes a begin and an end and some code that it will execute on every element of the collection, just like a for loop. So you might be tempted to think that you can replace all your for loops by for each, and that you'll be done. That you'll be using the STL algorithms. And that's not quite the spirit, because there's much more than for each in the STL algorithms library. There's many more algorithms that let you express more nuance when you write your code. I'm going to show you something to illustrate the fact that there's much more than for each in the STL algorithms library. Ladies and gentlemen, I present you the world of the STL algorithms. On this map, I've placed all the STL algorithms as of C++ 17, and I've grouped them by region according to the logical relationship they have, right? The rest of this talk will consist in exploring that world. But before diving in, we can note a few things while looking at it from afar. The first thing we can note is that for each is just one of them on one island lost on the middle of the ocean. So it's just one of them. What we can know also is where most of them are. You can observe that the largest region on that world is over here, and that's the lands of queries. We call that queries because all those algorithms that live here, they just read into the collection and extract some piece of information, and they don't actually modify it. I don't know what you think, but I would have thought that most algorithms would somehow change the collection, like sort or partition or whatever. Like, they are there as well, but most of them, they're just read-only operations. I suggest that we start our journey by the other end of the world from for each, down here on the algorithms on heaps. So what is a heap to begin with? A heap is a data structure that looks like a tree, but that has a property. It's that every node must be smaller than its children. I think it's called that because it kind of like looks like a heap in real life. Like the small ones are at the top and the bigger one is at the bottom. It's better having a heap. Now you can observe that the heap on the right of the picture is the other way around, right? The biggest element is at the top and every element is bigger than its children. That's a C++ heap. It's called a max heap. The relationship between the parent and its children is the parent is bigger, right? So it's the other way around from the heap from real life, but you know, we developers don't really live in real life anyway, so does it really matter? I don't think so. So one interesting property of a heap is that we can squash it down into a range, like that. One more time, more slowly. To squash down a heap into a range, we take the first row, which is just the root of the tree, and then the second row, and then the third row, and so on and so forth. And when we do this, there's this nice property that it's arranged, so we can represent it with a vector, for example, which is quite convenient to work with. And also, to go from a node to its left child, it's essentially taking its index and multiplying it by 2. It's nearly that. So it's a way to represent a tree into a range. If we have a range, we have a beginning and end, and we can use STL algorithms. So the first thing we can do is taking values that are not particularly a heap and rearrange them so that they respect the heap property to make a heap. To make a heap, we use std make heap with a beginning and end, and that rearranges the element inside of a collection. That's our first algorithm of the day. That's 1 down, 104 to go. I forgot to mention, it's 105 STL algorithms in less than an hour each. Just making sure we've got the same understanding here, right? No, I'm joking. Don't worry. Well, either way, you'll find out. Let's move on. What we can do with a heap is add something to it. Independently from C++, to add something to a heap, we put the new thing right at the end, and it might not be its right position because it may be smaller than its father. And the way to add it to the heap is to swap it with its parent until it reaches its final position, right? Now, to do that in C++, we can squash down the heap, right, to represent it as a range, say that it's a vector. We add something to the end, and then we need something to make it bubble its way up to its final position, and that's push heap. Now, push heap just does the same thing we've seen with the tree vision, but in the range vision. Now, to remove something from a heap, well, there's this thing with heap. Why do we use heaps in the first place is to be able to get the maximum value of the collection in not too much time, in constant time. Like the heap, the max element of the collection is just the front. So this is what we access, and this is also what we allow to remove. To do that, we swap it with the last one. That's what pop heap does. At this point, the range in yellow is probably not a heap because that's the one at the end that was probably one of the smallest ones that was at the beginning. So we need to make it bubble its way down to its final position, and that's what pop heap does. And if we want to actually remove that value, we pop it back from the vector. Now, if we don't pop it back from the vector, but leave it here, and do that again for the part in yellow, the shrinking heap. If we do that over and over, at the end, we'll get, can someone see what we'll get at the end? Yeah, right, a sorted collection. So that's a way to sort a collection, and that's what sort heap does. Talking about sorting, this is the region around the corner, the shore of sorting. So let's see how to sort with the STL. Well, the simplest way probably is stud sort. That takes a collection, begin end, and rearranges them so that they're in sorted order. Okay. Now, if we only want to sort the beginning of a collection, as we saw in depth in Fredstock, we can just partial sort the thing. So partial sort takes the beginning and end, and sort of like a middle, something inside of the collection, and sorts the collection from the beginning to that point, and the rest is in unspecified order, right? So the left-hand side of the collection is what would be there if it was completely sorted. Now, to sort just one element, that's nth element, which takes a begin, an end, and something inside of the collection, and puts at that position inside of the collection the element that would be there if the whole thing was sorted. And for the rest, everything that's on the left is smaller, and everything that's on the right is not smaller. There's sort heap, which we've mentioned with repeatedly calling pop heap, and there's in-place merge. In-place merge is the incremental step in a merge sort. So we've got a collection that we can mentally think of as two halves, and merge sorts. So the two halves are sorted, and merge sorts combines the whole thing into a sorted collection. So that's about sorting with the STL. Just further up the shore, there's the region of partitioning. So what's partitioning in the first place? To partition a collection is to look at it through a predicate, something that returns a Boolean. Here, our predicate is being blue. To partition a collection is putting all the blue ones at the beginning and all the not blue ones at the end. Of course, it works for blue and red and yellow and actually any predicate there is. The border between the blue ones and the not blue ones is called the partition point. That's the end of the blue range, and that's also the begin of the not blue range. Can you see that? Okay. That's called partition point, and to retrieve it from a partition collection, there's stud partition point. Right. If we take a step back on that part of the world, that was the land of permutation, the place where elements move around the collection, even if they don't change value. We've seen heaps, sort, partition, and there are a few others that we'll go through quickly. There's this permutation that takes the element at the end and put it at the bottom. Put them at the beginning, sorry. That's rotate. Another way to change the order of the element of a collection is to do that randomly. And that's what stud shuffle does. So stud shuffle takes a collection with elements in a certain order and takes something that generates random numbers and rearranges the collection in random order. There is an order we can define on permutations. Like given a set of objects, given a collection of objects, we can order them, order all their possible arrangements, and an intuitive way to see that is thinking about an alphabetical order, right? So in this collection, 1, 2, 3, all the way to 9, the smallest one, if those were in a dictionary, would be that first one, 1 all the way to 9. And the one just after would be the same thing with a 9 and an 8 swapped together, right? And so on, and the largest one will be the one at the bottom here, from 9 down to 1, right? If you have a collection in a given order, any order between the smallest and the biggest one, next permutation, which takes a beginning and end, would rearrange it so that it goes to the order that's just after it, and pref permutation to the order that's just before it. That's interesting if you'd like to do something for every possible arrangement of a collection. You can repeatedly call next permutation until you've cycled back to the beginning. And finally, the last one is reverse. That reverse is the element of a collection. Right, so we've been all around the lands of permutation. Just in the corner of the map here are the secret runes. The secret runes are things that you can combine with other algorithms to generate new algorithms. I call them runes because it's like going to see runes to augment your powers, and also because I find that kind of cool as a name. So let's call them that purpose of this presentation. We've seen all the algorithms that go with the stable rune. So stable, when you tack it on to an algorithm, it does what this algorithm does, but keep the relative order. Think about partition, for example. It put all the blue ones at the beginning, that's for sure. But maybe in the process, some of them got swapped around. With stable partition, they all keep the same relative order. Same thing with stable sort. The is rune checks for a predicate on the collection. We know what sort, partition, heap means, or is sorted, is partition, is heap, returns a Boolean to indicate whether it's a sorted, a partition, or a heap that we're looking at. And is until returns an iterator that's the first position where that predicate doesn't hold anymore. Right? So for example, if we have a sorted collection and we call is sorted until, we'll get the end of that collection. All right, let's take a step back. So we've been down there in the lands of permutation. Let's now focus on the largest part of the world, the lands of queries. There are quite a few of them in there, but we'll go through them quite quickly. So one thing you can extract out of a collection is some sort of value. For example, the simplest one is probably count, that takes beginning and end and a value and returns how many times this value occurs in the collection. There's accumulate, that makes the sum of the element of the collection, calling operator plus, or any custom function you'd pass it. In C++17, there's reduce that appeared, that does practically the same thing as accumulate, except it has a slightly different interface. It can accept to take no initial value, and it can also be run in parallel, but essentially it's the same as accumulate. And transform reduce takes a function and applies that function to the element of the collection before calling the reduce. Partial sum, well, it sums all the elements starting from the beginning to the current point of the collection. So here, partial sum would return a collection with, in the first position, what was in the first position of the original collection, and in the second one would be the first one plus the second one. In the third one would be the first plus the second plus the third, so on and so forth. In C++ 17, there's inclusive scan, exclusive scan, transform, inclusive scan, transform, exclusive scan, which have interesting names, let's say. Well, inclusive scan is the same thing as partial sum, except it can be run in parallel. Exclusive scan is the same thing as inclusive scan, except it doesn't include the current element. So for example, with the exclusive scan, the second element would be equal to the first element of the original collection. The third one would be 1 plus 2. The fourth one would be 1 plus 2 plus 3, and so on and so forth. And the transform versions of those two guys take a function, apply it to the collection, and then perform the including/exclusive scan. Inner product makes the inner product of the collection, which is a multiplication of the counterpart elements, and then summing that whole thing. Adjacent difference makes the difference between every two neighbors in the collection. And sample, appearing in C++17, takes something that can return, that can generate random numbers, and it takes a number, say n, and it produces n elements of that collection selected randomly. Apart from querying a value, we can query a property. Well, there's all of, any of, and none of, which are really useful in everyday code. All of takes collection and predicate, returns if all of the elements satisfy that predicate, any of if at least one element satisfies that predicate, and none of if no element satisfies that predicate. Now, what do you think all of returns with an empty collection? What do you think? Fred? True. Does everyone agrees with Fred? Yeah, that's true. Any of on an empty collection? Yeah, false. None of? Come on, there's only two possible answers. Yeah, true. Absolutely. That was querying a property on one range. We can also query a property on two ranges, which is essentially different ways of comparing them. The simplest way to compare two ranges is to see if they have the exact same contents. So the element would be equal 2 by 2, and it would have the same size, and that's what std equal returns. It returns a Boolean. Now, if we'd like to know if the two collections contain the same element, but not necessarily in the same order, that is permutation, also returning a Boolean. Now, we can also compare ranges and say which one is smaller than the other one. To define smaller, we could go with size, but that's not very precise. There's another way to do that, is going back to the alphabetical lexicographical ordering, right? Like in this example, I've used characters, but that can be with any type that has a comparison operator. You can see on this example that the left collection is smaller than the second one, than the right one, if they were in a dictionary, right? Even though it's longer in terms of size, it would come before in a dictionary, and that's what lexicographical compare returns in the form of a Boolean. Now, the last way to compare two collections is to traverse them both and stop whenever they start to differ. That's what mismatch does, std mismatch, and it returns a pair of iterators pointing to the respective position where they start to differ in the two collections. Now, a classic thing to extract in a collection is a position, like looking for something. Well, to look for something in a collection, there are essentially two ways to do that. It depends on whether the collection is sorted or not sorted. If it's sorted, we can use a binary search. If it's not sorted, we have to go all the way through from the beginning. Let's start with the not sorted case because it has the lower number of algorithms. Well, the simplest one and very famous one is find. Std find takes a value, a begin and end value, and returns the iterator where pointing to that value. Now, or end if that value is not found. Now, it has a sort of like twin brother that's much less famous but quite useful as well, and it's called a JSON find. And that returns the first position where two adjacent value occur and are equal to the value searched. So JSON find takes a begin and an end and a value and returns the first position where two of those values appear in a row. On the sorted side, we are not really looking for a value because searching for a given value could be at several places, and since it's sorted, they would be lumped together, right? So in this example, if we're searching for orange, we're actually looking for a subrange that could be empty if orange is not there at all, and that's what equal range returns. To search in a sorted collection, we use equal range. There are other algorithms that sort of like look like it, lower bound and upper bound, and they only indicate positions to insert elements. Like if I were to insert a new orange, at the left of the existing orange, I would use lower bound, and at the right of the existing orange, I would use upper bound. And there's this guy, binary search, that returns a Boolean, which is a bit unexpected, because it takes a begin and end and the value, and only tells you whether it's there or not, but doesn't tell you where it found it. And it uses a binary search, which is a good thing. Now, we've been looking for one value in a collection, like orange. We can also look for a range of value in a collection, like looking for the first occurrence of a subrange in a big range, like looking for that range on the left in the big range. To do that, there's an algorithm that has a very bizarre name because it's called search. I don't know what you think, but for me, search is almost the same as find, except find says that it will find it, right? And search says it will try to find it. But search has nothing to do with find. It searches a subrange into a range. That's not the best name. I think the most curious name in the whole STL library is what follows, which is looking for a subrange, but starting from the end. It's called find end. That's good to know, isn't it? And what we can search in a subrange is any of the value in the little range, finding its first occurrence in the big range, and that's find first of. And finally, we can search for a relative value, which is the largest one or the smallest one. That's max element or min element, or both. Min, max element that returns a pair of iterators pointing to the max and the min, the min and the max element. Right, we've been around the largest part of the world. Now we're going to move in my favorite place. It's the glorious county of the algorithms on sets, because they're glorious. Well, what's a set to begin with? It includes std set, but not only. In C++, what we call a set is any sorted collection. So a std set is sorted and is a set, but a sorted vector, for the purpose of the STL algorithms, is also considered as a set. Set difference, which is my favorite algorithm, takes two sets and returns the elements that are in the first one, but not in the second one. And its interface is like that. It produces its output via an output iterator. I like it so much because it's useful all the time, and it's also in linear complexity. And it would be easy to implement in quadratic complexity, but it's in linear complexity because it uses the fact that the input are sorted and also its output is sorted. Set difference has siblings. Set intersection, that returns elements that are both in A and in B. Set union, that returns elements that are in A or in B, so everyone. Set symmetric difference, which is, I think, the longest name. Yeah, it's the longest name in the whole library. Fun fact. That returns the elements that are in A and not in B, and those that are in B and not in A. Includes, that returns a Boolean that indicates whether all the elements of B are also in A, and merge. That takes two sorted collection and puts them together into one big sorted collection. Oh, that's it. What was that? Too short. Okay, let's take a step back. We've been in the most populated regions of the world, all over here. We now have just these parts, small parts to cover. So maybe we'll take an hour after all. So let's go to this place, the place of movers. So movers are algorithms that move things around. The simplest way to move things around is probably to copy them. So std copy is probably the simplest algorithm in the whole library. Takes takes one collection with a beginning and an end, and the output iterator of a second collection, or back inserter, or stream iterator, or whatever, and copies every element of the first collection into this output iterator. There's also std move. Like, we know std move, but there's also std move, the algorithm. And it takes a beginning and end and an output iterator, just like std copy, and it calls the usual std move on every element of the input collection. So after std move, the algorithm, all the elements of the input collection are moved. And to swap the contents of two ranges, there's swap ranges, and they all obviously have to be the same size. Now, a little exercise. Let's say that we've got a collection at the top, 1, 2, 3, all the way up to 10. And we would like to write some code and use an algorithm that we've seen from the beginning of that talk up until now to turn it into the collection at the bottom. So we want to copy the first 5 elements 4 positions down. Which algorithm do you think we could use to do that? Well, there's less than 105 possible answers. Yeah. Copy, absolutely. So we'll use copy. I thought to use copy as well. And then I think it crashed when I used it. So let's see what happens, what's happening. So the first thing copy does is to copy the first element, right, to the output. So I don't know if you were thinking about that, but I put as an output iterator begin plus 3. And then we've lost a value. We've lost 4, right, which is annoying. What we would like to do is to copy, but starting from the last one, right? Because we didn't care about the 8 that used to be there. And then move all the way back up, yeah? So what we would really like to do is to copy, but backwards. That's what we're going to say, right? Yeah, copy backwards. That's pretty much the same thing. And there's also move backwards that does the same thing, but moves. Right, so that's the movers. Now, just down around the corner, there's the value modifiers, which I would have expected to be more numerous, but there's just 4 of them in a quite large piece of land. So those guys actually change the values inside of a collection. So how can we change the values inside of a collection? One easy way to do that is to put the same value everywhere. That's what fill does. It takes begin and end value and copies that values all the way through. Another way that's a bit similar in spirit is to use a function that can be called with no argument, and we call that function once for every element of the collection. That's generate. Another way to fill a collection that's quite useful to have like, I don't know, unit test, stuff like that, to have quickly a sequence of values is iota, which has a funny name, I think. It takes begin and end value, put that value at the beginning, and then increments it until it fills the whole collection with increments. And finally, there's replace, that quite expectedly replaces the values in a collection. Like replace 42, 43 will replace every 42 by a 43 in a collection of ends. Right, now jumping above the water, there's this island of the structured changes. What I call the structured changes is the algorithms that after they've done that job, the collection doesn't look the same even from afar. So there are two of them, remove and unique. Remove is used to remove values, but it has something peculiar with it. Since STL algorithms only access the iterators of a collection and not the collections themselves, they can't change the size, for example, of a collection. They can't perform an erase in a collection. All they can do is to change the values between the begin and the end. So what remove does is to pull up the collection by leaving only those that should not be removed. So if we want to remove the 99s, we use std remove, begin, and 99, and it will pull up everything that's left without the 99. And what's at the end is not specified. We can't rely on it. It could be the element that were there before, it could be 99s, it could be anything else. It could change, it could vary from compiler to compiler, from version to version, so we can't rely on that. And to actually remove those elements from, say, a vector, we have to call a method on the container, like erase on a vector. We'd like to erase all the elements that are crossed out. And to do that, remove returns an iterator that points to the first element that's here crossed out. So we have to erase between what remove returns and the end, which is quite of a mouthful of code to remove the 99 in the collection, isn't it? I think that we should not use that code, and we should wrap it into a function with a nicer name and use this in our everyday code. I reckon there's been a proposal by STL, Mr. STL, the guy, to add those functions to the standard. It hasn't been accepted yet, so until it is, if it is, we should just wrap this function. It's quite another thing to do. If you want to grab the code, it's been published on free on C++ last week, I reckon. Unique does something quite similar. It removes the duplicates in a collection, or more precisely, the adjacent duplicates in a collection. Right? So if we do unique here, this collection has several 99s, and it will remove only the adjacent 99 because it has a linear complexity. It will only traverse the collection once. And unique will also pull up the values that are to be left and return an iterator to the values the values that are crossed out. Those values, we can't rely on them, just like remove. And we have to erase them, quite a bit of code, not much, and we should package that into a function with a better name. Whether unique is a better name, I'm not sure, but we should at least package that into a function. I've got a question there. Sorry, I couldn't hear that. Indeed, one was not removed. That's good observation, and it's not removed because there's no adjacent ones in the collection. Thanks for that. We've unlocked a new rune, copy. We've seen all the algorithms that are combined with copy in the STL algorithms library. So copy, you can tack it on an algorithm like those algorithms, and it creates new algorithms that do the same thing, but in a new collection. So like remove or unique or replace or whatever, they operate in place. Those guys, they leave the collection untouched, and they take an output iterator and they produce the output to that output iterator. We've also unlocked if that as a predicate, so where, say, find, for example, was taking a value, find if takes a predicate, but does essentially the same thing. And we're going to go to that part we started with the talk with, the Lonely Islands, with for each and transform. Let's start with transform. There's nothing wrong with for each transform. The reason why I put them on Lonely Islands is because I couldn't see in what family they would belong. I think they sort of like separate, even though it's not a problem in itself. So transform essentially applies a function to the elements of a collection. So it takes a collection, big N, a function, f, and an output, like an output iterator, such as this back inserter here. And it produces the application of that function to every element in the collection. What's a bit less famous about transform is its other overload. The one that takes two collections and a function that takes two parameters, right? So it applies that function just like transform with one input collection to the two collection by feeding the two collection into F for each element and producing the output. Yeah, like for example, if you'd like to sum the elements of two collection 2 by 2, you can do that with one line of code with transform, and F would be stud plus. And that's for each. And for each, if we think about what it does, so for each takes a begin and end and some piece of code, a function, it could be a lambda, for example, or a regular function. And it applies that function to every element. What's interesting to note is that it doesn't care about what F returns. So for the purpose of for each, F might as well return void. Now, what does a function that returns void do? Anyone an idea? Yeah, exactly. Side effects. For each is made to perform side effects. Now, are side effects a good thing or a bad thing is absolutely not the purpose of that talk, even though I think that some cases are useful with side effects. But for each is made for doing side effects. That could be side effects on the elements themselves, modifying the elements of the collection, or that could be side effect in the more general sense of sending stuff to logger or whatever, right? But for each is made for side effects. Using for each for making anything else, such as a partition or a find or whatever, is not the right usage of for each. There are algorithms that are more appropriate than for each. And if there's no algorithm more appropriate than for each in the STL algorithms, then there are algorithms outside of the STL library, and we briefly talk about them in a minute. Okay, so we've been literally all around the world. We've started down there, we've been in the land of queries, the glorious quantity of algorithms and sets, movers, the value modifiers, and the structure changes, and even up there. There's only one place we haven't been yet, the raw memory. So we're going to finish up with that one. What does that mean? Algorithms and raw memory. Well, if you think back to fill and copy and move, they have one thing in common. Does anyone see what they have in common? Is that they use the assignment operator. For each assigns a 4 to 2, fill assigns a 4 to 2, copy assigns with the copy assignment, move assigns with move assignment. They all use an assignment. Now, if we use an assignment operator, it means that the object has been constructed, and hopefully that's true. But in some rare cases, we have objects that are not constructed yet. If we have just the memory, just chunks of memory that we got from somewhere, and we'd like to construct instead of calling the assignment operator, we'd like to call constructor on those chunks of memory. Well, for that, we use an initialized counterpart, an initialized field, initialized copy, initialized move. And those use constructors. So this is the constructor that takes a value. This is a copy constructor. This is a move constructor. So in practice, you get a chunk of memory from somewhere, like shared memory or wherever. And you'd like to fill it with values, but you can't call fill because you can't call the assignment operator because it's just raw memory, right? It hasn't been initialized yet. So we need to call the constructor. This is what an initialized fill does, right? It takes 2 pointers at the beginning and the end and calls the value constructor, leading to an initialization of that chunk of memory. Now, once we're done with it, we want to call the destructor of those guys because we've been in charge of their constructor, probably also in charge of calling the destructor, and that's what std destroy does. Kind of like, sounds familiar, right? Destroy, but we don't really use it on a day-to-day basis, but that's what it does. So destroy will destroy call the destructor of all the elements in that collection. And if we'd like to call the other kinds of constructors, such as default constructor or value constructor, value initialization, because an initialized default construct, initialized value construct, and we've unlocked our final rune, the _n, that changes a little the interface. Like instead of taking a begin and an end, it takes a begin and a size. Let's take an example. So still using fill. So fill takes a begin and end value, put that value all the way through. Fill n takes a begin and a size, okay, and a value, and it fills the first 5 elements starting from begin. It fills them with the 4 to 2s. Now, what do you think this third line of code does? Imagine that collection is a vector, an empty vector, for example. What do you think is in collection after executing that third line of code? Say that a little louder.
Insert 5 elements of 42?
Absolutely. That would insert 5 elements equal to 42, right? Because it would assign through the back insert operator 5 times. Right, this time we've been around the world, everywhere. You know everything in the STL algorithms library. Now what? Well, for one thing, you can use them in your code to make it more expressive, right? You can think about, if you want to write a for loop, think about if you could use an algorithm instead, or if you could replace existing for loops that are like a bit of a problem in your code by an STL algorithms to make it smoother to work with. And if you'd like a second pair of eyes, I always like to read code. So you can reach out to me and show me your code, and if you can have a look and think about which algorithm with you we can put in your code, I'd be more than happy to look at code. If you'd like to see more algorithms, there are some outside of the STL, and the library next door is Boost. There's Boost algorithms, which contains all the algorithms that are in the same spirit as the algorithms of the STL. Soon I will publish on Fluent C++ a series of articles going through all these guys. To go further, it's a good thing to understand in depth the STL algorithms. I think it's a good investment of our time about their complexity, about their prerequisite, post-requisite. Think about sorted collections, for example, and see how they're implemented, and that's often quite instructive. And finally, if you use them on a day-to-day basis, you can get inspired. You can have a better intuition of what abstractions work well. And that's fundamental for writing good code. And that intuition, you can use that in your own code. And once you're familiar enough, you can start thinking about writing your own algorithm. So what sort of algorithm can we write? Well, we can combine an existing algorithm with an existing room to create a new combination, like sort copy doesn't exist, for example. Or we could add a city on the map. If I were to add something, I think I would add something to the algorithm that sets. Do something like an algorithm that would have 3 outputs. Those are in A, not in B, B, not in A, and both in A and B, or in a single pass, I think. I'd add that. If you think about things to add, I'm happy to hear about that too. Or start a new family. If you'd like to get the map, you can download it on fluentcpp.com/getthemap. And there you can also order the poster that you can hang in your homes and offices. And for the people in the room, if you'd like to acquire a poster right now, like those ones, I've got a bunch of them with me, so you can come and see me after the talk. If you'd like to get in touch, you can find me on Twitter @Boccara. And if you're interested in reading about the STL or about expressive code in general, you can check out fluentcpp.com, Fluent C++, with a new post every Tuesday and every Friday about expressive code in C++. Thanks.